balloons and rockets, astronomers have successfully launched telescopes into Earth orbit above the distorting effects of the atmosphere. To explore deep space, NASA has had great success with robotic probes like Voyager that have observed and sent back images of our solar system. NASA and its partner, the European Space Agency, are now on the verge of launching a huge optical observatory into orbit around the Earth. Hubble Space Telescope will see objects even near the edge of the known universe with 10 times finer detail than possible from the ground. At the heart of the observatory is an 8-foot mirror ground to near perfection. When pointed at an object, the mirror collects light and sends it to 6 instruments. Various satellites and ground stations relay the instruments' information to the Space Telescope Science Institute in Baltimore, Maryland. Viewing screens will allow scientists to make real-time observations. At the same time, a tremendous amount of data will be generated, according to Dr. Eric Jason.
We're talking about a huge amount of information. In fact, we colloquially refer to this as drinking from a fire hose.
In order to help astronomers plan observations, the Space Telescope Institute has the largest star catalog in the world, containing 19 million celestial objects. The catalog was made by scanning over 1,400 photographic plates of the entire sky. The plates are also stored in a giant database, so astronomers can call up a region, like the Andromeda Galaxy, and manipulate the images with false color. In our lifetime, space telescopes should match the discoveries made since the beginning of astronomy.
We hope to see, in the words of Galilei, wondrous things. Those were the words that he used in 1609. We want to see star systems. We want to see images of the planets. But in particular, Space Telescope is designed to look out into deep space, to study deep space astrophysics, to go out to a realm that we've not yet been able to study well.
In 1990, Shuttle Discovery launched NASA's Hubble Space Telescope, the most powerful observatory ever built, able to image detail up to 15 billion miles away. Hubble has provided astronomers with a clearer window to our universe. Soon after Hubble was deployed, scientists discovered an aberration in the 94-inch primary mirror. Even so, the huge spaceborne telescope has been returning a steady stream of new information, particularly with the aid of computer enhancement. Similar processing has been used on data from other spacecraft, like Voyager, which traveled past the planets. Enhancement now brings out more detail for Hubble scientists. This is the telescope's original image of a galaxy 52 million light-years from Earth, as it is cleaned up to its final version. Here, light pulses in a straight line between Earth and a distant quasar. Years ago, Albert Einstein suggested that if a uniform object crossed the path, light would bend into a ring. But if the object were not uniform, the ring would break up into 4 patches. Known as the Einstein cross, Hubble's image reconfirmed this part of Einstein's theory of relativity. Hubble also showed scientists a celestial X, marking the exact spot of a black hole with the possible mass of 1 million of our suns. Astronauts are already training to fix the Hubble mirror problem during a shuttle service call scheduled for late 1993. By substituting a special component in the telescope, the aberration will be repaired. Called CoStar, this corrective optics package contains a series of mirrors that work like contact lenses to restore Hubble close to its full imaging potential. In a clean room at NASA's Goddard Space Flight Center, technicians also practice removing the spacecraft's star tracker, which helps point the telescope.
Yeah.
In the meantime, Hubble continues to send back fine detail of the planets, faraway galaxies, black holes, and distant stars, rewriting the textbooks on how we view our universe.
The science team knew that the best from the newly restored Hubble Space Telescope was yet to come.
Come on. The purpose of today's press conference is to present and explain the first images from the Hubble Space Telescope.
And I'm happy to announce today that after its launch now in 1990, some of its earlier disappointments, the trouble with Hubble is over.
It's often said that a picture is worth 1,000 words. In fact, these corrected images are as perfect as engineering can achieve and as the laws of physics will allow.
For NASA, at the beginning, it had been tough to be the first, then tougher still to stay at the front, and now, toughest of all, to come from behind.
We sure appreciate your playing that downlink for the planning shift. It's nice to know what we're really working on. Yeah, you betcha. You guys are real important. We appreciate the work. Our pleasure.
I've never seen the teamwork I've seen in this program. People have pulled together from all the centers, Johnson, the Kennedy Space Center, Goddard, headquarters, contractors, because I think deep down, people realize, because of what's happened, this program is part of history.
To fix a telescope already in space, the team had to diagnose the optics problem from the flawed images, then build replicas of the telescope to develop, test, and retest the corrective optics and replacement hardware.
It was really exciting to see all the work that I had done manifested in the test, because I spent 2 years preparing to actually test the CoStar in system functional, and to have it all work like we had planned was really wonderful.
We had to build mock-ups of every part of the servicing mission, including the science instruments, and complete mock-ups of the equipment going into the cargo bay of the shuttle.
What we're doing now is verifying that the camera is going to play properly with the rest of HST, that it's going to fit into HST, and that it's also going to be commanded properly by the ground system and talk to the computers on board the HST properly.
To prepare, the astronauts and servicing teams planned, modified, and endlessly practiced each task using a variety of training techniques.
Every time we set out to think through a task, during every step along the way we go, well, what if that doesn't work? What if this happens? What if that happens? And for each one of those what ifs, we need to have a plan.
Before the actual spacewalks, astronaut Story Musgrave predicted what they would face.
For every subtask, I've looked at the things which are the most delicate and require the most really critical care. The rate sensing units, placing them on, they have very narrow tolerance, placing those on the 2 pins.
And I guess, Jeff, you'll be going back to Sorka 10 and Power Tool 3 next time.
And on the solar rays, I think it is making the electrical connectors.
Okay, it's staying there perfect. Great job.
Wide field planetary camera, it's taking the mirror off in a very careful way, and then protecting that optics, which is right out there in front of your face. The CoStar is big as a telephone booth, very square, and it's got to get into the rails exactly right.
Wonderful. Hold her good, KP. And did he bring you up a little? Would that be all right? Yeah, just directing. I can't. Okay,
all the careful planning really paid off during the mission. The crew and ground team even had prepared for surprises. When a broken solar array wouldn't roll up for storage, Kathy Thornton jettisoned it as the sun rose.
Hey, go ahead.
It was caught like a sail on the wind of the shuttle's jet plume.
That looks like a bird, Tom. Look at it. down, hold.
The mission sharpened Hubble's sight and NASA's vision.
We're actually building up our abilities to work in space. We're laying the groundwork for the future.
The Hubble is our eyes. It's how we're going to see back to the beginning of the universe. It's how we tell what's happened to us in the past and where our universe is going in the future.
Safely to the Earth. Made engine start.
Right away, here, sir.
NASA's Hubble Space Telescope has opened a window on our future, with this image released at the American Astronomical Society meeting in Tucson, Arizona. The structure of the Cat's Eye Planetary Nebula reveals to astronomers the death throes of a star like our sun.
So in some sense, when we look at an object like this, we're looking at the future of our own solar system.
Our solar system would be a tiny speck in the enormous gas cloud imaged by Hubble. And Earth, like any planets this star might have had, would be vaporized.
Moving around here, yes. And shooting material out. And the same here. Well, it's possible that all this structure. moving around here, yes, and shooting material out. And the same here. Well, it's possible that whole the structure actually was produced by a jet.
In fact, you could have had the jet producing this structure out of the end.
That's right. And look at those little tiny knots. That's where the jet ended.
Right. How fast is that jet?
Previously.
Because this represents the last stage in the evolution of ordinary stars, a star like our own sun, is going to go through an episode of this sort in maybe 5-6 billion years from now. So in some sense, when we look at an object like this, we're looking at the future of our own solar system. If this star did have planets, they would have been vaporized early in the stages of ejection, and they're not there anymore. It was clearly the best image of a planetary that I have certainly ever been involved with and that I've really ever seen. And I remember stopping on the way home from looking at this and saying, we've got to get a bottle of champagne and have a toast, because this is a spectacular image. I think it's beautiful for the same reason that it's interesting, which is all the symmetry in it. I think that this is probably the most exciting image of a planetary that I have seen, because of the level of complexity and detail that we see here. It's really quite unprecedented. Other objects are simply messy, but this one has got all sorts of fascinating structure. Well, this is a planetary nebula. Planetary nebula is sort of a misnomer, actually. It's the sort of gas cloud, the fireworks that are produced when a fairly ordinary star reaches the end of its life and throws its outer layers into space. The reason they're called planetary nebula is because in the last century, when people were using small telescopes, some of the small round ones looked a little bit like the planets Uranus and Neptune in our solar system, and that's how they picked up that name. But really, it is the cloud of gas which is produced at the end of a star's lifetime. What we see here is a record of a multi-stage process. The actual loss of the outer layers of the star turns out to be enormously complicated. We can see that at the present time, the star is blowing a bubble. It has a wind which is flowing rapidly into space, and this tenuous fast wind is sweeping up the nebular material and constructing a bubble. But outside of that, we see this ring of knots, which must correspond to some earlier stage of ejection. And further beyond the boundary of the picture that we see, there's actually an outer halo. Furthermore, the jets that we can see in some of the images represent the very rapid phase of mass loss which occurs after the main structures have been formed. So it's an extremely complicated process. For a specialist like myself, there's an enormous amount of detail that's going to tell us about many things. It's going to tell us about the kinds of elements that were created in the last stages of the star's life. It's going to tell us about the ejection process itself. It raises interesting questions about how these jets can form in the last stages and then change their direction suddenly. But from the point of view of just the average person, I suppose you could say that it's interesting because it's a window on our own future. It tells us what is going to happen to a star like the Sun in a very long time.
Or tell me what you're putting in.
I've got it removed.
Okay. Okie dokie, we can go up, Mark, and start thinking about the position to stick this puppy in. Bad thing about this is, Ron, you can cheat and look through it.
Yeah, I understand. But you wouldn't do that, Tom.
You can't keep from it.
I know.
Look at the big picture here.
Okay. Looks fairly
looks
level
good
to me, yeah.
Looks good.
Okay, let's drop me down now, Mark, a little bit. Gently. Don't take me any forward so I can keep pressure in it here. Just drop me straight down.
Okay, now I can apply pressure back here now. I've got it on the handrail.
Okay, let's go down, Mark. Let's just wait till I get in position now, Jeff.
Okay. Okay, I've got it.
I want to get over on this left side now.
I've got it a good hand on it. You can even let go if you have to.
I want to watch this guide rail. Go ahead and drop me down, Mark.
Can you see the guide rail up there?
Yep, that's what I'm getting down to. Yes, I can.
Okay.
Coming down, Mark. Coming down, Mark. Okay. I'm happy. Just easing in.
Okay, we're back at the end of the forward guide rail. We've got to lift it up a little bit to get onto the aft guide rail.
Okay, come on down then, Mark.
Now I can move inside and help with this if...
Okie dokie. Okie dokie.
Here I come. Are you clear?
Yeah, I'm going to help you here. Okay, I got it. Okay, Mark, keep bringing me aft now. Keep some pressure on the doors. For Jeff here.
Possibility that it's cocked slightly.
Okay, it's coming now.
Okay, Story.
Yes.
Remember, and Kathy, when you get about 5 foot out, we want to stop, take a picture. Okay.
And KT, you want to put a tether on it? I got it.
I have a tether.
Okay. Okay.
Okay, am I clear? Am I
yes.
Right level?
Yes, you got it.
Okay.
She's coming straight out. Have at it. Okay, it's clear.
Okay, want to do a picture time here?
No, I think he wants you out a little further.
Okay.
Be 5 quarter turn T-handles.
Yes.
EV2 Kathy, you're going to translate the HSP to the aft fixture at the ORU carrier and temporarily stow the HST by engaging the 1 pit pin on the top fork. Now this does not slide in sideways, this slides in from the top.
Slides in from the top?
Yes, ma'am.
That may
Okay,
be
let's see,
real.
that's the bottom over there.
Hanging up on there.
You got it in right. If you were to take it down now, you're okay, Kathy.
Oh,
That's the
okay.
way you want it to go in. I'm talking about down on the aft fixture. It's
Oh,
slicing.
yeah, I see the one hook. Yeah, got it. Okay. And if you could roll me 90 to my left, Mark, and then go down. I'll come in on my side. And if, well, that is if the RMS is going to clear that forward fixture. I won't be able to tell you that. Okay, you can go aft about a foot.
Oh, I guess I'll run my slide.
Okay, and outboard. I need to go outboard. Port.
Do you need me to scoot over there, KT?
Stop port. Aft. A couple feet.
Hey, Story, you can
Yes.
help. You're going to...
The other glove is better, actually.
They were mine.
Where is the PSA exactly? Is it between? Oh no, it's forward of the solar right now.
You reach down there and get those top two pip
Or if
pins
you are a little
down.
too high, it doesn't really matter because this is where we would take you from there on. You would start the GCA. If it is, you think far too high to start the GCA.
Yeah, let me do that now. The stanchion needs to be over to this, around to the right.
The other...
Doesn't want to, stanchion, there we go. Can we open the radial sight? Okay, well, that's okay. We're positioned basically over it.
You can touch...
Ease me in, Claude.
You're going to have to lift, there's riding up on the rail. Now you need to lift up just a little bit to get it up on this rail down here.
Now, KT, can you transition to the L handle?
You ought to be able to help down there now, KT.
Yeah, that's if I can't push much. I'll make it in here where I can.
Okay, hold on a second. Bring your end out a little, KT. We're pitching in at the bottom. You're way ahead of me down there. Okay, bring me down, Claude, a foot. Down, Claude, thank you.
Right, wait a second here, Tom.
That's good, stop.
On something here where I can help.
Okay. Okay, let's stop right there. Okay, KT. Got to bring your end out, KT.
One out, okay.
All right.
Yeah, budget.
Okay, now drop me down, Claude, where I can get more on the seat. You can't push any.
I can't push or pull here.
Hang on a second. Okay, bring me up, Claude. Stop. Bring me up, Claude. Stop. Oh, we had a strap hanging down. That might be real world.
What's it hanging from?
Who knows? Bring me up a little more, but it's in the way. Okay, bring me up, Claude. Stop. Now they say we're okay. Now, KT, can you look at it and see yaw-wise if we're okay?
Presently, the technicians, the SIFIC crew, are attempting to align the co-star into the extender rails and adjusting for pitch, roll, and yaw to make sure that the co-star is correctly aligned with the rails prior to inserting into the Hi-Fi mechanical simulator. Well, they'll have to make sure that the rails capture the co-star guide blocks and rails, and so that when the co-star is correctly aligned, it will insert all the way into the OTA in space.
what they'll do is put it in just a little bit and juice it in. And that's it.
They put a stop in there. Do you remember why?
3, 2, 1, and liftoff of the Space Shuttle Discovery with the Hubble Space Telescope, our window on the universe.
In 1990, ESA and NASA launched the most powerful astronomical tool ever built, the Hubble Space Telescope. Since then, astronomers have been making observations which are at the forefront of space science. In December 1993, Space Shuttle Endeavour will link up with Hubble in orbit to carry out a space mission never before attempted. Astronauts will make several spacewalks, during which they will service the key components. One of their first tasks will be to replace the solar arrays, the power behind the Hubble Space Telescope. Hubble has some 50,000 individual solar cells mounted on its two 12-meter-long solar arrays. Each cell receives energy from the sun's rays and converts them into electricity. Since the launch in 1990, the arrays have successfully produced a reliable 4.525 kilowatts of output. This electricity is used to power the telescope's scientific instruments and communications systems. The cells are glued to a blanket, which expands and contracts as the spacecraft orbits in and out of the sun. Radiation and other processes, such as atomic oxygen erosion, however, gradually degrade spacecraft, and in particular, the sensitive solar cells. After 4 years in space, the arrays are coming to the end of their useful lifespan, and like a further 49 key components of Hubble, they were designed and are ready to be serviced and upgraded where necessary. The scheduled servicing mission has given ESA the opportunity to redesign the solar arrays in order to cure a curious problem. Extremely rapid temperature changes during sunrise and sunset, together with some friction effects, are causing uneven movement of the system of pulleys and springs. These compensate for the expansion and contraction of the blanket. Additional movement is being detected at the drum, where the blanket is anchored. At the same time, the temperature changes cause the side-supporting booms to bend. This stick-slip movement causes a slight jitter at the observing end of the telescope, the pointing control system. When Hubble observes a distant celestial object, it does so with minute accuracy. The jitter, although very small, has an obvious effect. Imagine looking through a pair of binoculars whilst traveling along a bumpy road. Up to now, engineers have minimized the effect of the jitter by using special computer software. But this takes up valuable memory capacity within HST's onboard computers. To make this capacity available for scientific purposes and to correct the stick-slip movement, a deceptively simple and elegant design solution has been found. The mechanisms linking the supporting booms to the array blankets have been replaced with simpler structures. The blanket is wrapped around the end boom, and when the sun rises and sets, a system of springs allows the blanket to expand and contract. At the drum, a simple brake mechanism is used to keep it still. The side support booms are covered by a special concertina-like thermal shield, which almost eliminates bending by greatly reducing the day-night temperature differential. Apart from these modifications, British Aerospace Space Systems, ESA's European solar array contractor, has used the same basic flight-proven design for the replacement solar arrays. At British Aerospace, the solar arrays are being checked out during their deployment on a water testbed to minimize the effects of gravity. This is the final test before their launch in December, and also a chance for 5 of the 7 Shuttle Endeavour astronauts to get to know the mechanics involved in deploying the arrays.
My role during this exchange of the solar rays will be to support the extravehicular activity of my American colleagues by moving crew members at the tip of the arm to the proper location to do their job, to pick up the solar rays in the solar ray carrier in the cargo bay and bring them to the place of work to fix the solar rays on the Hubble Space Telescope. And of course, before doing that, we'll have to remove the old solar rays and put them in the cargo bay.
The new design and replacement of the solar arrays is a key element in the first service mission of the ESA-NASA Space Telescope. This and future planned missions will continue to enhance the high sensitivity needed to observe distant stars and galaxies.
The Hubble Space Telescope, the largest, most sophisticated space astronomical observatory ever launched by NASA. Its data has already rewritten much of what we thought we knew about our universe. Launched in April of 1990, it carries 5 scientific instruments to look at the universe in both visible light and the ultraviolet wavelengths. One of those instruments, the Goddard High Resolution Spectrograph, or GHRS for short, was built by Ball Corporation's Aerospace and Communications Group in Boulder, Colorado. During orbital checkout, however, a flaw was discovered in the telescope's primary mirror that blurred the images, enough to reduce the image quality to some instruments and require computer enhancements. It was determined that the giant 94-inch circular mirror had an edge that was 1/10,000th of an inch too low. The telescope had been designed for on-orbit maintenance and repair over its 15-year life, including replacement of instruments, but the giant mirror was another story. Then, a group of scientists, including optical experts at Ball, developed a design for an instrument that might correct the flaw. When NASA decided to build this instrument, Ball was chosen as the prime contractor. Ball's aerospace group produced the instrument, called COSTAR, in just 26 months, about half the time considered routine for a space instrument of its size and complexity. COSTAR is short for Corrective Optics Space Telescope Axial Replacement. If all goes as planned, Space Shuttle astronauts will capture the telescope and perform a variety of tasks on orbit. One of those will be installing COSTAR. Once inserted into place, COSTAR will extend 5 pairs of mirrors into the light path between the flawed mirror and 3 other instruments. In each pair, the first mirror images the distorted light onto the second mirror. The second mirror is designed to correct the flaw in the telescope's primary mirror. But by far, the most demanding part of this mission will fall on the crew of Endeavour. Astronauts also will have to install new solar panels, a new wide-field planetary camera, and install an electronics repair kit on the GHRS. That's why in March of 1993, the crew came to Ball's Boulder, Colorado operations for some visual and hands-on training with COSTAR and GHRS. The astronauts inspected COSTAR and discussed how to handle and install it, as well as testing the tools they will use. They also gained experience with the electronics kit for the GHRS. The upcoming Space Telescope servicing mission will no doubt be one of the most exciting and challenging ever attempted, and Boulder, Colorado people will be playing a major role.
After launching it into space, NASA and the nation realized the Hubble Space Telescope had a perfectly smooth yet flawed mirror. The NASA team's challenge: find the prescription and restore precision optics on a spacecraft already flying. To fly what you test and test what you fly would be easier if the telescope were back on Earth. But landing and relaunching could contaminate the telescope or damage it through vibration. NASA couldn't test the new corrective optics in the actual telescope. So to make sure the optics will work, the team had to determine the condition of Hubble in space and replicate that on the ground. One independent review panel used Hubble images to determine the precise shape of the flawed primary mirror and the prescription to fix it. Another team had to verify that the corrective optics will work. Teams had to test two optical packages: the replacement wide-field planetary camera and the corrective optics for the other instruments, called COSTAR. Engineers built several independent analyzers to test that they had replicated what the Hubble telescope does to light. An independent team here at Ball Aerospace measured both sets of optics, then remeasured the measuring tools. For mechanical testing, engineers built a simulator at Goddard Space Flight Center using the same precision equipment that built Hubble originally. The corrective optics and the new camera attachments were installed so that their locations duplicate the telescope attachments within 6/1000ths of an inch, the thickness of a piece of paper. The clearances are even tighter in the simulator than they will be on the real telescope to assure a margin of safety. To replicate Hubble during electrical tests of the corrective optics package and the new camera, an electrical test facility was built with the same schematics as the original telescope, and it too was audited by an independent team. All three, optical, mechanical, and electrical, were merged together in a test of the whole system. Data from the test were sent to the Space Telescope Science Institute, just the way data will be sent from the telescope. Hardware has been thoroughly tested on the ground. The Hubble servicing team is preparing for contingencies. But this mission is a first, so no one can predict everything that could happen. The real test will be in space.
T-minus 10.
Landing a man on the moon,
8,
returning him
7,
safely to the
6,
Earth.
main engine start.
Right away, Houston.
This will slip at 10 foot now. Okay. Is there a big difference between here?
One parallel, which takes
You guys ready? Ready.
Go ahead. Coming around number 2. Push it back on.
Well, neutral buoyancy, I mean, having been EVA, you get up there and you go out into Palo Bay and you think you're right back in the pool. I mean, it's just as realistic as you can get, and being able to float around like you do in the suit. So that's the real advantage of it, is you can train almost exactly like being in space. You have a little bit of drag from the water, but you're able to move around the bay, test out the tools. We make the tools neutrally buoyant also, so you don't have a lot of weight, and it just gets you very well prepared to do the job in orbit. Well, I think everyone remembers the last Hubble repair mission, and what we're doing right now is we're going through a series of possible tasks that they're going to do on a second servicing mission. So what we're trying to do is see if we need new tools, new equipment, and that's the real reason we're here, is see if we have any long lead items to get ready for that second repair mission. And then later on, probably by the end of this year, they're going to decide exactly what tasks we're going to do, and the next series of runs and on in the next year will be specifically looking at those tasks and training the crew to do that.